Hi dear students. So in the last lecture we have discussed about the scalar multiplication and as well the work done and the kinetic energy and the work relation, the work energy relation. So in this section we will discuss about the kinetic energy and as well the work done by a variable force and the work energy relation, work energy theorem, and the derivation of the work energy theorem. These are the things that we will discuss in this chapter. So first of all, the kinetic energy. Actually, as the name indicates, the kinetic energy means the energy of motion, energy due to the motion, movement. Actually, the kinetic energy is a scalar quantity. You know that. For the energy, we don't want to consider the direction. The kinetic energy of a body or object can so the kinetic energy of a body is actually the measurement of the ability of a particular body to do work due to the virtue of its motion. That is known as the kinetic energy. So kinetic energy of an object is actually the measure of work can done or work can be done by a body by the virtue of its motion. That is known as the kinetic energy in the case of a particular body. And suppose if a body of mass m and which it is moving with a velocity of v, the kinetic energy will be given by the equation, that is kinetic energy is equal to half of the product of mass with the product of mass and the square of the velocity, that is half m v square, half of the product of mass and the v square, the square of the velocity. So here the kinetic energy value will be equal to half m v square. And as well, for many applications we are using up the benefit of the kinetic energy. So there are the kinetic energy of a fast flowing stream has been used to grind corn, and as well sailing ship employ the kinetic energy of the wind. Now let us come to the example number 6.4. The question is that in a ballistic demonstration of police officer fires a bullet of mass 50 gram. So the mass of the bullet it is 50 gram, that is 0.05 kilogram with a speed of 200 meter per second raised to -1. So the velocity is equal to 200 meter per second raised to minus 1. So on a soft plywood of thickness 2 centimeter, the bullet emerges with only 10% of its kinetic or initial kinetic energy. What is the emergent speed of the bullet? So after the reflection, what would be the speed of the bullet? First of all, you have to find out the initial kinetic energy. Initial kinetic energy value will be equal to half of the mv square here m value it is 0.05 and the velocity v is equal to 200 the whole square is actually 40,000. And in the question itself it is given that after the collision the energy of the bullet became only 10%. So the initial energy we can take that one as 1000 joule, and afterwards after the collision the energy remained it will be 100 joule. So half mvf square, actually the final velocity that you have to find. So half half mvf square will be equal to 100 joule. So by substituting the values in that equation, the Vf value will be equal to 633.2 meter second raised to minus 1. So the initial velocity it is 200 meter second raised to minus 1 and the final velocity will be 63.2 meter second raised to minus 1. You can find out the percentage, how much percentage it is. As you are calculating the percentage value, the 63.2 meter second raised to minus 1 is actually 68% compared to that of 200. Now, the work done by a variable force. You know that if the force value, if it is a fixed value, throughout the part, if the force is fixed, then only the displacement will be a variable, will be considered as the variable. So the work done will be equal to force into the displacement value. Whichever the displacement, the work done, if you want to find the force value into that displacement value, then you will get the work done for a particular displacement. But if the force value is continuously varying throughout the path, so for the first one point, for first t1 time, the force was F of x1, take that one, and the displacement is considered to be x1. Then after, we are not considering the time, okay, after a particular second or after a particular time, for a distance of x2, the force value will be is equal to F of x2. Again, for a particular point till x3, the displacement it is x3. So first one it is x1, second one the displacement is x2, and third one x3, where the force value is F of x3. So if you want to find out the total work done there, the first one will be F of x1 dot x1, okay, plus F of x2 dot x2, likewise plus F of x3 dot x3. If more numbers were, then more various forces were there for the displacement, then you have to add up all the forces, product of all the forces and displacement. Means individually you have to consider the work done for particular displacements, and you have to take the sum of those. So we can say that is in general, if you are having an initial position xi and a final position xf, then the total work done will be is equal to summation of xi to xf f of x delta x, where f of x is a function of x and the delta x is the displacement. As the displacement changes, the f of x value also will change. For a particular displacement, the f of x value will be maybe if it is fixed. For that distance, the work done will be is equal to the force value into the displacement. Again, for the next displacement of x2, if the force value, that some other value will be there, maybe it can be increase or it can be decrease. On the basis of that, the force into displacement there also you have to do, and afterwards you have to take the sum. Okay, now suppose, actually this is the case of a discrete force distribution. Suppose if it is distributed continuously, then means the displacement between these two, the displacement between these, suppose the x1, x2 and x3, where f1, f2 and f3. Okay, suppose if the distance between these points are getting almost similar to 0, that means very negligible, it will become very negligible. There the discrete function we cannot use, we will be using the continuous distribution. Okay, continuous distribution means instead of the summation you have to follow the integration. So substituting the limit delta x tends to 0, in the sense the delta x is almost equal to 0. That means the time interval is very less or least. Okay, so limit of delta x tends to 0, summation of xi to xf will be is equal to, xi to xf of f of x dx will be is equal to integral xi to x of f of x dx. Okay, so we can say the work done for a varying force means as the displacement changes, the force value is also changing continuously, and where the displacement value delta x is approximately equal to 0 or it is tending to 0. So the work done for a varying force can be expressed as the definite integral. Definite integral means in between the limit initial point xi and a final point, and that's why the definite integral. There's a limit is there, so in between xi initial point and a final point you have to take the integration for the force over the displacement. Okay, so that is another definition for the work done by a varying force. In the integration case, the displacement is approximately equal to 0. Okay. Suppose if you are given with the force displacement graph, the area under the graph, okay, the area under the graph will give you the work done. So here you can see the first graph, or for the first or second graph, in both the cases, the force is not constant. Okay, throughout the displacement from a point to point. Suppose if you are considering the points are here, that is initial, and suppose consider these are the 2 points you have considered. In between, the force value is varying like a straight line like this. It is varying. That means as you want to find out the area, the shape will be a trapezium type shape you will obtain. So it will be difficult if you continuously considering the area under the graph. This will be the area under the graph. Actually, we cannot find out easily the area of this particular diagram, isn't it? For this particular shape, it will be difficult to find out the area, so we are just dividing this one into various blocks. Okay, various rectangular blocks. You're just dividing this entire area into the form of various rectangular blocks, where each rectangular boxes, the y-axis will be f of x, and the x-axis will act as delta x. Okay, x-axis will be delta x and y-axis will be f of x. So integration of these things you have to do, that is integral of if it is a discrete function, if the displacement delta x value is almost similar to 0, that means for a slight variation of displacement there is an increase in finite increase in the increase or decrease, or finite variation is happened there in the case of the force. So in such cases you can use the integration. Okay, so integration f of x dx. Likewise, you can find out the entire area of the entire area covered by the graph. So the area covered by the graph always gives you the which graph? Force displacement graphs. Okay, so area under the force displacement graph always gives us the work done, the amount of work done by that force for that particular displacement. Okay, you have to remember this one. And one example, I think 6.7, that example is regarding this theory portion, that is the area under the graph you have to find. By using the area of the graph, you have to find out the work done by that particular force. Okay, just go through that one. Now for a constant force we have derived. If the force is constant, then the work energy theorem, actually the change in kinetic energy will be is equal to the work done. And so where the work done will be is equal to F into F dot D, where the F is the constant force we have applied throughout the path of movement, and D is the displacement obtained. And the work done due to this displacement will be displacement by applying that force. For this displacement by applying that force, the work done will be is equal to F dot D, and that will be is equal to the final kinetic energy minus that of initial kinetic energy. So the energy loss which was happened to the particular block or particular body will be is equal to the work done by that body. Okay, so these things was clear in the case of the constant force. Now, if the force is variable, then how can we derive this equation? How can we use this equation? Or how will be the format of this equation? That we are going to discuss now. So you know that K is equal to mv square by 2, or the half mv square is equal to the kinetic energy. Okay. Now you have to take the rate of change of kinetic energy with respect to time. That is d by dt of half mv square. Where half m is a constant, so you have to write, or you have to find the half m of d by dt of v square. Actually, you know that the v square is actually a function of, that is v is a function of time. Okay, but v is not directly related to time, but v is the function of time. So we can actually d by dt of v square, there will be a variation as the time changes, there will be a variation in the v square also. So first of all, you have to consider the entire term, that the v square, and thereafter you have to consider the v. Okay, so d by dt of v square will be, first of all, for the v square, there is the d by dt of t square. You just consider d by dt of t square, where d by dt of t square is actually t raised to n, that is t square, that is n into t raised to n minus 1. That is for the square value. That is for, if in the case of here the n value it is 2, so 2 into v 2 raised to, v raised to 2 minus 1, that is 1, into, actually in the case of the t itself, there is actually the d by dt of t square is actually 2t dt by dt, but where dt and dt are same, so that will become 1. Here also you have to do the same. D by dt of v square is actually equal to 2v into dv by dt. Okay, from कहाँ से ये 2v कहाँ से आया? From where you got the 2v? That is actually the differentiation of v square. That is d by dt of v raised to n. Suppose instead of 2, if some other value was there, then d by dt of v raised to n will be is equal to n of v raised to n minus 1. So where here in the case of n is equal to 2, so 2v 2 minus 1. So that is 2v raised to 1, 2v. And afterwards you have to take the differentiation of v itself. So that will be dv by dt. So you can see, after the differentiation, m, actually it is half m into 2v into dv by dt. So where half cancel, m into v into dv by dt, m into v into dv by dt. Okay, m into d into dv by dt. So that is actually the rate of change of kinetic energy with respect to time. So now, where the dv by dt is actually the a value, acceleration. Okay, so m into a into v will be there, m into a into v, where m into a is force, so force into velocity is actually the dk by dt. We can write the force into velocity is actually dk by dt. So here the force into velocity, where velocity is actually as a function of displacement, the velocity is actually is equal to dx divided by dt. Okay, dx divided by dt. So substituting the v as dx divided by dt, so the equation will become, that is f v Fv will be equal to F into dx divided by dt. F into dx divided by dt. Now on both sides the dt, dk by dt is there and f into dx by dt is there. So the dt will be cancelled, the time variable that you will cancel, and dk will become equal to, that is dk will become equal to f dx. Now you have to integrate both the side with a limit initial xi and final xf, integral of xi to xf, where xi is the initial position and xf is the final position xf. Okay, now by integration the dk will become k. So by the limit, applying the limit, it will become kf minus ki. So integral of xi f dx. You know that integral of xi to x of f dx is actually the work done, isn't it? Integration of the force with the, or force upon the displacement, that is actually the work done. So here again we have derived the kinetic energy change, where the kinetic energy is actually depending only, that is the kinetic energy of the final point, and the difference in the kinetic energy of final point and kinetic energy and the initial point, that is kf minus ki, will be equal to the work done, where the whatever the value of kinetic energy in between the path, that we are not considering, not at all considering, only the kinetic energy at the final point and the kinetic energy at the initial point. These 2 points are only we are considering, and that variation, that change is actually equal to the work done. Okay, that much only. So study these things, go through the textbook, read the textbook line by line thoroughly, and the example questions are given. Actually, after studying a theory portion, for confirming that theory portion, the examples are given. Okay, so after studying the theory, just to go through the example also. First you just try to solve that one as your own. Okay, and thereafter you just take the help of the solution which is given with the example questions. So wish you all the best. Thank you.